Hi, welcome to es301 Engineering Analysis. This is Chapter 1 on Mathematical Model. Here are the learning goals. At the end of this, you'll know the attributes and limitations of what we call a mathematical model. We will review some important aspects of differential equations. You'll understand the difference between an analytic and a numeric solution to an equation. You'll know how to apply Euler's method for numerical integration. And then we'll review some important conservation laws that are used in engineering. So first I want to go ahead and talk about mathematical modeling. And one of the important things that I think is actually most intriguing about being an engineer is that engineers are really designers. I look up a definition of a designer, and here's one from the web. It says, a person who plans the form, look, or working of something before it's being made or built, typically by drawing it in detail. So it's a good definition of a designer. And another thing I really want to point out is this word here, before. What you need to do is we need to be some way to be able to go ahead and predict how things are going to behave. And that's where mathematical models come in. So for example, imagine that you were designing some brand new plane that doesn't exist. And so what you want to do is you want to be able to determine how this is going to behave. And what you'll end up using are mathematical models that will describe many, many aspects of this thing that does not yet exist, but you want to go ahead and design. So let's just talk a little bit about mathematical models at a very high level. And a mathematical model is usually in the form of an equation, and that equation has kind of a more general form where you've got some sort of dependent variable. This is the thing that we want to know. It might be the lift force or the drag force, something like that. And then it's going to be a function of many things. And so usually we can break up those things that is maybe a function of its independent variables. And a lot of times this is the space and location that the object is operating in. There might be a set of parameters, and those parameters might be, for example, how large the wings are, what the pitch of the wings, the depth of the wings, all sorts of stuff. And then there might be like forcing functions. For example, what's the wind velocity that we have that this plane is experiencing. So how do you come up with a mathematical model? Well, usually the model equation is determined by combining some fundamental physical laws, things like Newton's law that you learn in physics, with some empirical observational data. And empirical just means by observations. This statement here is a little redundant, and usually you're running a bunch of experiments. So for example, you might want to know how some particular wing is going to behave, and it's very tough to go ahead and predict that from fundamental physics. It's usually best to go ahead and do a test, stick it in a wind lab, and determine how it behaves. So, for example, let's just go ahead and look at this plane, and say we were trying to determine what the lift force was on this. And so we might end up out there doing a lot of analysis to determine that maybe it's a function of, in terms of its independent variables, where it is located in the atmosphere. So maybe that is some weird function like 3.2z over z plus 1, where z is the elevation. And then we need to maybe multiply that by some parameters. It might be the length of the wing, and maybe plus 2/3 of the depth of the wing, some parameters that are how large the wings are on this plane. And then we might find that we have to then go ahead and multiply that by something related to the velocity. It might be 1.2 times the velocity that it's occurring to the 1.31 power, some strange value that we went ahead and measured in the wind tunnel. All right, so we had some sort of combination of some physical laws relating to lift, and then some observational data that we had this very complicated equation of what the lift force is. And the lift force, we realized that right there would be, for example, the mass of the plane, and then it would be the change in velocity with time. So we have dv dt, and what you realize, if I was to go ahead and reproduce everything I wrote up here, we're going to have something that's, again, a function of v. So this is going to be a whole bunch of stuff. And notice I've got the velocity that's in there as well. So what I end up with here is a differential equation. It says how v changes, and how v changes is a function of v. So I'm going to talk a little bit about differential equations. And this is not a mathematics course, so we won't really be required to solve many differential equations, but it's important to know kind of where they all fit in. And so I'm going to go and get away from that somewhat complicated made-up example I had of the plane and look at something a little more simple. This is what's discussed in the textbook, where we have this skydiver, and he reaches jumps out of a plane and accelerates and then reaches a terminal velocity. And the book goes ahead and gives you this differential equation where v is the velocity of the skydiver, and it says that the change in velocity with time of the skydiver, dv dt, is equal to this right here. This is the mass of the skydiver, g is the gravitational constant, and c is a drag coefficient, and there's the velocity of the diver. So realize that we've got a differential equation because I have dv dt, the differential of velocity, and then it's a function of velocity. And I can go ahead and cancel out the m's in this term, and I just kind of rearrange the equation that I have it right there. Right? So this equation, this is a differential equation, and you may be able to solve it or not, and that's okay. I'm not going to require you to figure out how to solve it. The book gives you the solution. Here's the solution for what velocity is. Velocity is a function of time, because here we have dv dt, so it says that velocity changes with time. I integrate it, I apply an initial condition, and I have what the velocity is as a function of time. So right now, sort of there is where time is in that exponent. And we also, when we solve these problems, we need to know what was called a boundary condition, or in this case, it would be an initial condition. And that initial condition was that at time equals 0, so when he first jumped out of the plane, his velocity was equal to 0. And in fact, if we look at this equation for the velocity of a function of time, I realize that this is true. So for example, if I look over here, e to the 0, well, because if t was 0, this would be the exponential of 0. E to the 0 is 1. I have 1 minus 1. That whole thing is going to be 0. So clearly at t equals 0, v is equal to 0. I can also look at an extreme, so at the time of a really large number, so maybe at 100,000. And so then I would have e to the whatever c over m is times 100,000 minus 100,000. That ends up being effectively 0. That second term is 0. So I have 1 minus 0. It's just 1. And so I find out that my velocity is equal to gm over c. So it's going from 0 to this value gm over c. And so there'd be some intermediate time. So maybe at time t equals 10, I would have a velocity, and it would be some fraction. I don't know. I'm making up a number here. Let's just say 1/2 of gm over c. So it's going to go from 0 to this value here as time progresses. And you could go ahead and plot this. Just go ahead and stick it into maybe Excel. And I could go ahead and plot what the velocity is as a function of time. The origin is 0, 0. I'd find out that it would look like this, and it's going to approach a value over here at very large values of time, which is gm over c, and that's called the terminal velocity. And at that point, dv dt is equal to 0, and I reach the steady state condition. So this is a solution, an analytic solution to a differential equation. Right? So let's go ahead and talk about a numerical approximation. So maybe you don't know the solution to that equation, or you're not able to solve it. So either way, we could go ahead and do what's called a numerical approximation of the solution. There's various ways to do numerical approximations. I'm going to discuss here a method called Euler's method. So let's go back and remember the definition of a derivative. The definition of a derivative actually is the change in that top parameter, so it would be the change in velocity over the change in time as the change in time goes towards 0. But here we'll just talk about a finite change in time. This would be delta v over delta t. And so that right there would be equal to, well, mg minus cv over m. Right? And so then the change in velocity over time, I could write that as a velocity at some time. I'll call that time I plus 1 minus the velocity at time I. So I is just a counting variable. Goes 0, 1, 2, 3. It's the number of seconds. And that's going to be all over my delta t, which would be t at I plus 1 minus t at I. And that's my delta t time. And so it might be better for me to actually use kind of approximately equal, because since I'm not doing finite changes, I don't have a differential. It's not an exact solution. So now what I could do is, remember my initial condition, we know that at time t equals 0, v is equal to 0. And now what I'm going to do is I'm going to go ahead and just do this at for example, we'll say time is equal to, well, the first one will be delta t, so that will be time at the first increment, and I'll call that v sub 1, so I'll call that v sub 0 for the first time, and v sub 1, and so look, imagine doing v1, so I'm like setting I equal to 0, so I have v1 minus v0 over this time here, and so that's going to be equal to m times g minus c times v, and this is actually, the value I know is v sub 0, so I'll put v sub 0 in there, over the mass right there. And since now I'm going to go ahead and multiply that by delta t. to go ahead and get what my change in velocity is. So now I can go and determine what v1 is, and then I can go ahead and keep doing this. I'm going to do time at time delta t times 2, for example. I would find v2, and then I'm going to go ahead and put in this equation, but this time I'm going to put v1 into that term. And I could find all these values of v, and I could go ahead and plot that. So now I've got some discrete values of velocity as a function of time. Might have a point there, a point there, point there, where each one of these is delta t, and I could go ahead and just kind of put these into a spreadsheet. I'm going to go ahead and get my values that I go ahead and move through there. And so now what I have, if I connected these points, notice I never solved the differential equation. I never had to determine what it was. I just did this kind of finite approximation to it. And my values would be somewhat equal to, if I was to look at, for example, sorry, I'm going to go back to what the analytic solution was. So maybe that dashed line is the analytic solution. I'd find out it's not exact, but it would be somewhat close. Okay. Now, I can go ahead and do this in a spreadsheet. So let's go ahead and do this briefly in an Excel spreadsheet, what I just described. If I can pull this open here. All right, so what I've done is I've set up an Excel spreadsheet. I've kind of started it off. And so here on this first column, I have time. And the second column, I have velocity. And I have my initial conditions. I entered 0 in there. And then I entered some parameters over here, and I labeled them to remember. So here's the mass, 68.1. These are some values out of the textbook, so we can verify we do this right. There's gravity, my friction coefficient, 12.5. And then we're saying dt is, for example, 2. So what I'm going to do now is I'm going to go ahead and put in my equation for dv dt. And so dv dt, remember, is equal to, well, I have g, and g, I'll go ahead and use that parameter. So I'm going to go ahead and put that in f2, and then minus, and then the value of c, I have in f3, and I need to go ahead and divide that by the mass, which is f1, right? And then I want to multiply that by the velocity. Here I'm going to multiply it by the cell that's right next to it, so that I can go ahead and update as I go through. So there's what dv dt is. So now I'm going to say, well, what is t? Well, t is going to be equal to the previous time plus dt, which is that parameter that I'm storing in f. It's in f4. Right? So there's my time. And so then what's my velocity? Well, my velocity is going to be the previous velocity, so it's going to be equal to the cell above it, plus, and here's my numerical approximation, it's going to be dv dt, right? And then times dt, that change in time, and so it's going to be in f4, right? So there I've got what my new velocity is, and so I'm just going to go ahead and copy down what that cell is, and then I can go ahead and just copy all of these cells downward. So first let's go ahead and have our times increment down. So there I'm going to go ahead and do that, and then I'll go ahead and copy these cells downward as well. All right? And so now what I realize is I've got this numerical approximation of what the velocity is as a function of time. So as time gets large, I've got, realize my numbers here are a little, let me go and just manually fix those really quickly, but we go ahead and realize what our times are going to be as I kind of briefly fix my time values there. There we go. That we're approaching a finite terminal velocity of around 53. Right? So that's how you do that in an Excel spreadsheet. Okay. One of the things you might wonder is, why would you ever do a numerical approximation? Remember, we just said that we had this differential equation we were able to solve analytically. Well, what if we had an equation that looked like something crazy like I show here, where now my value of c isn't some constant, it's got some sort of huge parameter mess times v over m. And if you tried to solve that analytically, you'd find out it's very difficult. And so where might that equation come from? Well, here what I have, this is a plot of the drag coefficient. So it's right here is my value of c. And it's a function of something that's called the Reynolds number. If you've taken fluid dynamics, you know that this right over here is more or less what the velocity is. And so this right over here is going to be the velocity times the length scale. Just go ahead and call that length scale L over the kinematic viscosity. But the key is there I've got my velocity term right there. So this is a function of c as a function of velocity. And look, even for a simple shape like a sphere, it's actually a fairly complicated function. It's not a constant. And you can only imagine now if you were to go ahead and draw what that is for a skydiver, it clearly isn't probably going to be some nice constant value like the flat plate, which is what we assumed before. We had this a value of c, probably be some sort of crazy looking function. And if I curve fit it, it might look something like this. So the reason we do numeric approximation is when we can't come up with an analytic solution, because the model equation that we have is so complicated. And this is very, very common in engineering. Normally, we're not interested in dropping flat plates out of planes. We're actually interested in people coming out of planes or something of complicated geometry like that. All right, so the last thing I just want to do is just kind of mention some conservation laws. And the reason conservation laws are important is because they're often in the form of differential equations. And so we end up, when we're solving engineering problems, we're applying conservation laws, getting differential equations, and then we go ahead and need to numerically integrate them. So conservation laws have kind of this general form. We might say that the change is whatever goes in minus out. So I can think of like a bank account. The change in money is the money you put in minus the money you take out. Or we might say the net of some values is equal to the summation of them all. So for example, force balance, right? We might say the net force is the summation of all the forces in some particular direction. So those are both kind of examples of general conservation laws. Let's look at a couple more specific examples. So here's the one that we just used in this problem, where we had we were adding in our gravitational force with our frictional force there. That gave us the net force, which was able to determine was the velocity, or the change in velocity with time times the mass times acceleration from Newton's law. So we applied Newton's law to go ahead and get at what our net change was there. Some other kind of common conservation laws you might have would be a mass balance, conservation of mass, where we'd say, okay, well, the amount of material going in minus what goes out of it is going to end up being the change of material inside a beaker. So yeah, a mass balance. Other things you can do that you can balance momentum. So maybe here I have a satellite, and it's got a thrust going in this direction, and maybe, I don't know, maybe this is some large galaxy that's actually got a gravitational attraction to it, and we can go ahead and do a momentum balance across that. Energy balances are real common ones. You run into this in thermodynamics and heat transfer, where you've got the energy going in minus the energy going out. You have that change in energy. So I've got some solar radiation coming in, reflecting off of here, and it's causing this to burn, and so then it's losing some heat by convection, as it's also combusting, and so there would be an energy balance term. You'd have a change in energy with time. And then in terms of maybe more in the electrical engineering range, a charge balance. So we've got the charge coming in and charge going out, and something's going to go ahead and accumulate charge over time. And those are 4 examples of conservation laws. It's not an exhaustive list, but it's a pretty comprehensive list of the things that you conserve. These are the fundamental laws that we apply to those mathematical equations. As I said, sometimes we need to go ahead and get those empirical equations, those kind of complicated parts when we've got more complicated geometries that happen. All right, so let's just go ahead and review what we talked about in this video. First of all, as we mentioned, mathematical models help designers, and remember, designers are what engineers are, to be able to predict system behavior ahead of time. Now, many engineering mathematical models can be expressed as differential equations, and this is why understanding how differential equations work is important to this class. And only a few differential equations can be solved analytically. There's actually a very, very small set of them. And that's what we would call an exact solution. And when we can't, then we have numeric solutions. And you can almost always compute a numeric solution using various techniques. This class is going to involve looking at many, many techniques for it. One I just discussed is Euler's method, and that provides an estimate of the solution to the differential equation. And one of the things to remember is it's never going to be exact. It'll always be really, really close, and we can get really close depending on how much computational effort we want to put into it. The best we can do is end up getting the analytic solution, if one exists. And one last thing just to remember is that conservation laws, which are things we use a lot in engineering, are often expressed as differential equations, and they can therefore be solved analytically sometimes, and otherwise we're going to have to solve them numerically using the techniques we learned in this class.